Today, we're going to learn how to read the stress life diagram. Now, in order to build a stress life diagram, we need to perform many fatigue tests at different values of stress amplitude. Each of those tests will have a corresponding cycles to failure, meaning the number of cycles that at that stress amplitude that test failed. Once we collect, say, several hundred of these experiments, we can plot that data as a stress life curve. Now, an important thing to note when we look at the stress life curve is that it consists of completely reversed fatigue data. That means these are tests where R is equal to -1. The maximum and the minimum stress are equal to each other and opposite. There's zero mean stress. We're going equal parts tension, equal parts compression. Now let's look at the stress life curve and let's diagnose what we see in this curve. Well, the y-axis is our stress amplitude, and the x-axis is the corresponding cycles to failure at each of our stress amplitudes. There are various regions that we can kind of highlight in this curve. Let's start with the low cycle fatigue region, where if we are less than 1,000 cycles or less than 10 to the 3, we have low cycle fatigue. Within this region, there tends to be more plastic deformation happening in our sample. There's local plastic deformation. It encompasses the ultimate tensile strength of our material. Somewhere between 1 and 1,000, the yield strength of our material exists. And so there is plastic deformation happening in this regime. Generally, under low cycle fatigue, we should be using the strain life approach, not stress life, right? Now, when we are greater than 10 to the 3 cycles, so when we have more than 1,000 cycles, a majority of this region has elastic deformation. Rather than plastically deforming, permanently changing the shape of our sample, we're just elastically deforming our sample. It's recovering back to its original shape. But over time, dislocation motion happens and we get fatigue failure. Now, for this high cycle fatigue region, anything greater than 10 to the 3, we can use the stress life approach. We can use the stress life approach, which we're going to learn. Now, there are another 2 regions that are of interest in our stress life curve. And one of them is the region that we call finite life. When we are between 0 and 10 to the 6, that's 1,000,000 cycles. This region is denoted as finite life. There's a finite life in our component. And that 10 to the 6 corresponds to something that we call the endurance limit, SE. It's a stress amplitude below which, in some materials, we'll start to see infinite life. Meaning if the stress amplitude is below that value, we can get 1,000,000,000,000 cycles, a Google of cycles, and never have failure. Infinite life. In steels, we tend to see that 10 to the 6 cycles, so 1,000,000 cycles. But for some other materials, it may span 10 to the 7 or even out to 10 to the 8, which is 1,000,000,000 cycles. And so sometimes in these diagrams, you'll see a little overlap between finite and infinite life. Now, we've got the basics of these different regions. Low cycle fatigue, less than 1,000. We cannot use stress life. High cycle fatigue, greater than 1,000. We can use stress life. Finite life, we're going to have a cycles of failure. Infinite life, we can cycle forever, right? And 2 key properties on our graph that are important are the ultimate tensile strength. This is usually obtained from a tension test, and it corresponds to 1/4 of a cycle. Because in a tension test, you just go up and your sample pops, right? But you've got to go through 0 3 times for a single cycle, so it's 1/4 of a cycle. And the endurance limit, SE, is a stress amplitude below which we have infinite life, and fatigue does not cause failure. Now, we mentioned that for steels and other alloys, that endurance limit sits at 10 to the 6 cycles. However, for many materials, particularly non-ferrous metals and plastics, they do not exhibit a sharp endurance limit. For example, we're going to look at some plots for aluminum alloys. So here is an example of some different aluminum alloys. And when we look at these alloys, when we're at 10 to the 6 cycles, we don't have that sharp knee. We don't have our endurance limit. In fact, we have a gradual transition that continues to decrease. And so often for aluminum alloys, as well as titanium alloys and plastics, we can see, we often see people will choose something around 10 to the 8, a billion cycles. In our textbook, we actually choose 5 billion cycles of reversed stress. And so if we go to our appendix and we search for some non-steel metals, we've got our aluminum alloys here. We see that in the description, it's 5 billion cycles. So 50 times 10 to the 7, 5 times 10 to the 8 cycles of reversed stress, right? And with that, we know how to read our stress life diagram.